Our topic for discussion today would be sets. Mathematically, it's what we call collection of objects which may be mathematical or not. Sets are essential when we're dealing with anything that requires us to collect specific objects. Sets are represented as a collection of well-defined objects or elements, and it does not change from person to person. For some examples, we can take a look at the collection of first 5 natural numbers, the collection of vowels of the English alphabet, the collection of whole numbers between 20 and 25. There are several types of sets. Let's look at subset. A set B is a subset of set A if every element of set B is an element of set A. For example, if set A has elements ABC and set B has elements BC, then B will be a subset of set A. If set B is a subset of set A, then set A will be called a superset of set B. For a proper subset, look here at the example. Set A has 3 elements of which only 2 are present in set B, making it a proper subset of set A. For equal sets, we see 2 sets that have same and equal amount of elements. Second type of subset is an improper subset, meaning that 2 sets have same elements and they are also equal. For example, set A has elements 1, 2, 3, 4, 5 and set B has also elements 1, 2, 3, 4, 5, making them an improper subset of each other. Another type of set would be a power set. Power set is individual sets of the subsets of any set. For example, if set A has elements 1, 2, then the power set of that would be a null set, a 1, a 2, and a 1, 2. How does a power set work? It has a simpler formula 2 raised to the power n, where n represents the amount of elements in a set. For example, if a set has 3 elements, then the n will be equals to 3, so the number of possible sets would be 8. Similar but slightly different to the equal sets would be equivalent sets, where the total number of elements are same, but the elements themselves are different. Null set has no elements, that is why it is also called an empty set. It is generated by a fire and also 2 curly brackets with nothing in between. A set that contains all elements of other sets that are being discussed is called a universal set. When talking about a null set, there is one thing you need to take notice of. First, every null set is a subset of every set, and other thing you need to know is that every set is a subset to itself and also equal and improper. Now moving on to our main topic for discussion, operations of sets. Sets has the following operations: union, intersection, difference, symmetry, and Cartesian product. In this video, we will talk about the first one, the union of sets. The union of 2 sets A and B is equal to the set of elements that are present in set A, in set B, or in both the sets A and B. Let's take an example. There are 2 sets A and B having elements 1 to 5 and 1, 3, 4 respectively. To perform the operation of union of sets, we will compile all of the elements and write them together, enclosed in curly brackets, keeping it in mind that no elements are repeated. Union of sets have 2 properties. The first one of the properties is that the union of sets follow commutative law, that is, A union B is equals to B union A. As you can see in the following example, we'll first perform A union B and then B union A. That will prove this property. Second property that union of sets follow is the property of associative law. That is, if we have three sets A, B and C, then A union B union C will always be equal to A union B union C. As you can see here in the following example, we'll first perform A union B and then union C, and then we'll perform A union B union C. The answer would always be same provided the elements are not changed. We have made a practice sheet for you to get better at the operation of union of sets. Several rules you must follow while doing any operation of sets is to make sure they are within curly brackets with no repetitive elements and should be in order.
Welcome back to our channel. In the previous video from our mathematics portion we discussed sets, types, offsets, and union of sets. In today's video, we'll move on to more set operations, and we'll cover intersection and difference of sets. So let's start. First, what is intersection? Well, intersection of two given sets is the largest set which contains all the elements that are common to both the sets, or the intersection of two sets A and B is the set of all elements belonging to both A and B. Let's take an example here so it can be better understood. Question: if set A equals 1, 2, 3, 4, 5, set B equals 3, 4, and set C equals 1, 6. Find the intersection B out by solving. We'll take set A and set B, write the intersection symbol between both sets, and now look for the common part or element, which are 3 and 4. So our answer for intersection B will be 3, 4. Now with the same question, let's solve B intersection C. We will write both sets B and C, place the intersection symbol in between and look for the common part. Here as you can see there is no common part, so the answer will be a null or empty set. Now, let's talk about some properties of intersection of sets. First is commutative property or law. It says that a intersection B is equal to B intersection A. So, let's prove it and consider two sets, A equals 1, 2, 3, 4, 5 and B equals 2, 3, 5. For a intersection B the common part will be 2, 3 and 5. Also, we will do the same steps for B intersection A. The common part will be 2, 3 and 5. Hence, the commutative law is proved. Second law or property is associative property, which can be written as a intersection B intersection C is equal to a intersection B intersection C. Let's solve an example to get a better grip on it. Take three sets, A equals 1, 2, 3, B equals 3, 4, 5, and C equals 5, 6, 7. First consider left-hand side and solve. A intersection B. The common part is only 3. Then take intersection of whole, that is, a intersection B intersection C. There is no common part now, so the answer will be a null or an empty set. Now consider right-hand side. First solve B intersection C. The common part is only 5. Now solve for whole, and again, the common part is a null set. Hence, the associative law is proved. The difference of two sets, written A minus B, is the set of all elements of A that are not elements of B. The difference operation, along with union and intersection, is an important and fundamental set theory operation. Let's use an example here. If set A equals 1, 2, 3, 4, and B equals 3, 4, 5, 6, then find A minus B and B minus A. Solving for A minus B, we will write both sets and use the minus sign in between. The common elements will be eliminated and only the remaining ones in set A will be our answer, that is 1, 2. Similarly, for B minus A, we will first write the set B, and then set A eliminate the remaining ones, and this time our answer will be the remaining part of set B. It can be noted that A minus B is not equal to B minus A. The topics we will cover in this video are complement of set and Cartesian product of sets. So, without further ado, let's start. The basic concept for the complement of a set is that it is the difference of any set from universal set. Suppose a set A, so its complement will be denoted by A with a comma and will be read as A complement. Let's take an example. There is a set A having elements 2, 3, and 4, and a universal set which consists all the elements present in other sets and some more elements. We have covered the topic types of sets in our previous video, so be sure to check it out first. So, as the question says, we need to find the complement of set A, as we know that complement of a set is the difference of universal set and the given set, which here is A. So, A complement equal to difference of universal set and set A. We will write both sets and write the minus sign in between. Now, as we know, when taking difference of sets, we will remove the common elements and will only take the remaining elements in the first set. That is, 2, 3, and 4 are common elements, so the remaining ones in the first set are 1 and 5, which will be our answer of the complement of set A. We will learn the concept of Cartesian product of sets through an illustrative example. To have a better grasp on it, suppose two sets A and B having elements 1, 2, and 3, 4 respectively. Since both sets have a total number of 2 elements each, so we will multiply both. That is, 2 multiplied by 2, which equals to 4, which means we will have a total number of 4 ordered pairs. So, let's make these pairs. First pick 1 and 3 our first pair, then 1 and 4. Second pair after that pick 2 and 3, third pair, and last 2 and 4, our fourth pair. Keep in mind that the pairs will be closed in round brackets, while these whole pairs will be close in curly brackets. In short, the Cartesian product is the making of ordered pairs, and it is denoted by a cross sign, in this case, A cross B. Let's solve a question here. A set A has elements A, B, and C, and set B has elements D and E. Find the Cartesian product of set A and B. First count the numbers of elements in set A and B, which are 3 and 2 respectively. For the total number of ordered pairs, multiply 3 and 2. The answer is 6. We will make a total of 6 ordered pairs. Let's start. First pair A and D, second pair A and E. Now pick B, third pair B and D, fourth pair B and E. Now lastly pick C, fifth pair C and D, and last sixth pair C and E. All these will be the Cartesian product of set A and B. We will complete our remaining topics from our lesson, sets, and our topics will be symmetric difference of sets and De Morgan's laws. We have already uploaded 3 videos, so if you haven't watched them yet, be sure to check them out. So without further ado, let's start. Symmetric difference is the set of the elements which belong either to or B, but are not common in both. It can also be expressed by A union, B difference, B intersection, A. It is denoted by a triangular symbol. Now, let's solve an example to understand the concept better. Suppose two sets A and B having elements 1, 2, 3, 4, and 2, 4, 6, respectively. For A symmetric B, we will eliminate the common elements, that is 2 and 4, and the remaining elements from both sets will be our answer, which are 1, 3, and 6. This is the short method for symmetric difference of sets. Now, let's solve the same question with long method, as we know that A symmetric B can also be expressed as A union B difference B intersection A. First we will solve A union B, and our answer will be 1, 2, 3, 4, and 6. After that, we will solve B intersection A. Our answer will be 2 and 4. Now in the end, we will take the difference, that is, eliminate the common elements, and write only the remaining elements of set A union B, which are 1, 3, and 6. As you can see, we get the same answer from both methods, so it's up to you which method you want to use. Moving on to our topic, De Morgan's laws. The first law states that the complement of union of two sets is equal to the intersection of the complement of these respective sets. Here, as you can see, A union B complement is equal to intersection of complement of A and complement of B. Let's take a question here. The universal set consists of elements 1 to 7. Set A has elements 1 and 2, and set B has elements 3, 4, and 5. Prove De Morgan's first law. Consider left-hand side. A union B. Our answer will be 1, 2, 3, 4, and 5. For its complement, we will take difference between universal set and set of A union B. Our previous video was about the complement of a set, so if you haven't watched it yet, be sure to check it out first. Our answer here for the complement of A union B will be 6 and 7. Now consider right-hand side, which is A complement intersection B complement. For A complement, we will take difference between universal set and set A. The answer will be 3, 4, 5, 6, and 7. We will repeat the same step for B complement, and the answer will be 1, 2, 6, and 7. In the end, we will take the intersection between complement A and complement B. The common parts, or our answer, will be 6 and 7. Hence, left-hand side is equal to right-hand side, and this proves De Morgan's first law. Moving on to our last topic, that is second law of De Morgan, which states, the complement of the intersection of two sets is equal to the union of the complement of these sets. Suppose sets A and B, so A intersection B whole complement is equal to complement of A and B. Let's solve an example here. Suppose a universal set having alphabets A to E, set A having elements C, D, and a set B having E as its only element. Prove De Morgan's second law. First, consider left-hand side. Take A intersection B. Since there is no common element, the answer will be a null or empty set. Now take its complement, and since there is no common element to eliminate, the universal set as it is will be our answer. That is, alphabets A to E. Now consider right-hand side. That is A complement union B complement. The answer for A complement will be A, B, and E, and the answer for B complement will be A, B, C, and D. Now take union of these, and finally our answer will be alphabets A to E, since left-hand side is equal to right-hand side. De Morgan's second law is proved. Thank you for watching. Hope you liked and learned something from the video. If you did, then give a thumbs up, comment down your feedback, and lastly, don't forget to subscribe. In today's video, we will discuss the periodic table and about how the modern periodic table came into being. The periodic table is a tabular array of the chemical elements organized by atomic number from the element with the lowest atomic number to the element with the highest atomic number. The aim of the classification of elements is to group together those elements which resemble each other in some respect, and to separate those elements which differ. The best classification will clearly be that which brings together elements which resemble one another in the greatest number of ways. We will talk about the scientist who helped in making the periodic table, such as Dobereiner with his triads, Newland's octaves law, Other-Meyer's classification, Mendeleev's periodic law and periodic table, and finally, the modern periodic law. In 1829, Johann Wolfgang Dobereiner, a German chemist, discovered that within a group of elements of three which resemble in chemically, the atomic mass of the middle element is approximately the arithmetic mean of other two elements. This is known as Dobereiner's law of triads, such as, the atomic mass of lithium is 7 and mass of potassium is 39. If we take arithmetic mean, then the answer will be 23, which is the atomic mass of sodium. The next attempt was made by an English chemist, Newland. Between 1864 to 1869, he arranged the elements in the ascending order of their atomic weights. He observed that properties of every eighth element is similar to the properties of the first one. He called this regularity law of octaves. As you can see, lithium and sodium are both alkali metals, and sodium is the eighth element after lithium. There are some advantages and disadvantages of law of octaves. For advantages, it provided a basis for the arrangement of elements which are similar in properties into a group. For disadvantages, this periodic arrangement didn't include noble gases, that is helium, argon, neon, etc., as they were not discovered then. Next is Lother-Meyer's classification. In 1869, German chemist Lother-Meyer classified 56 elements arranged in from groups 1 to 8. Meyer plotted values of certain physical properties such as atomic volumes against atomic weights and obtained some curves. From those curves he observed that elements with similar physical properties occupied similar positions, such as alkali metals lithium, sodium, potassium, etc. were at top, while halogens fluorine, chlorine, bromine, etc. were at the ascending part. Disadvantage or drawback of Meyer's classification were that Meyer's periodic table was incomplete compared with Mendeleev's periodic table, which was published in the same year with remarkable predictions. In the year 1869, Mendeleev, mainly on the basis of physical and chemical properties, discovered empirically a law known as periodic law, which he stated as, the properties of the elements are a periodic function of their atomic weights. Mendeleev arranged all 63 elements known at that time in order of increasing atomic weights. He arranged them in 7 horizontal lines, called periods, and in 8 vertical columns called groups. Merits of Mendeleev's periodic table were systematic study of elements. He made predictions of certain elements which were found to be amazingly accurate when the elements were later discovered. Mendeleev corrected the atomic weights of some elements, such as atomic weight of beryllium 13.5 was corrected to 9.4. There were also some demerits, such as position of hydrogen is not clear. Isotopes weren't assigned separate places. Mendeleev himself disregarded his periodic law in certain places. For example, tellurium 127.6 was placed before iodine 126.9. Dissimilar elements such as coinage metals, copper, silver, gold were placed along with alkali metals. In 1913, Moseley, a British physicist, established that atomic number is the fundamental property of the elements. On this ground, he stated that the properties of the elements are the periodic function of their atomic numbers. So how did the modern periodic law remove defects of Mendeleev's system? Well, it did have many weaknesses, but its main weakness was due to consideration of periodic law based on atomic weights, which was corrected by considering atomic numbers. Just like that, by basing the classification on atomic numbers, isotopes also got separate places. The anomalous placement of elements also disappeared automatically, and rare earth elements or lanthanides and actinides got place in periodic table. Here, I have attached the modern periodic table. You can apply all of the statements we studied in the start to see that all of those helped us in achieving this periodic table we see as of today and use for our ease. This video, the subject we will be talking about is chemistry, and our topic will be the 3 states of matter. But first, the question is, what is matter? The term matter refers to anything that occupies space and has mass, in other words, the stuff that the universe is made of. Examples can be from a solid pen, pencil to a mixture of gases that is air. The 3 states that we will talk about are solid, liquid, and gas. The liquid state. In a liquid state of matter, particles are less tightly packed as compared to solids. Liquids take the shape of the container in which they are kept. Liquids are difficult to compress as particles have less space between them to move. Liquids have fixed volume, but no fixed shape. Kinetic molecular theory deals with the properties of the particles, which are crucial in understanding the states of matter. From KMT of liquids, we can understand that the particles of a liquid are very close to each other, due to which a liquid has fixed volume. We can also note that the particles in a liquid are free to move, so they have definite shape. Now moving on to the properties of liquids. Number 1 is viscosity. It is defined as the internal resistance to flow of liquid. Factors which affect the viscosity of liquids are 1. The size of molecules. That is, if the size of the molecules is bigger, the viscosity of liquid is also greater. For example, since the size of honey molecules is bigger than water molecules, so honey is more viscous than water. Number 2. Intermolecular attraction. If the force of attraction between the liquid molecules is greater, viscosity of the liquid is also greater. Number 3. Temperature. A liquid's viscosity decreases with the increase in temperature, because by the increase of temperature, the molecules of a liquid move away from each other. As a result, the force of attraction decreases, and hence the liquid flows easily. Second property is surface tension. Surface tension is defined as force per unit length, acting downward on the surface of liquid. Because of the surface tension, a layer is formed which keeps lighter objects on it. Factors affecting surface tension are: Number 1. Intermolecular forces. That is, if the greater the force of attraction, the greater is surface tension. Number 2. Effect of temperature. By increasing the temperature, the force of attraction decreases, which results in the decreasing of surface tension. Number 3. The effect of hydrogen bonding. It points to the presence of hydrogen bonds between molecules, such as water has high surface tension due to the presence of hydrogen bonds in its molecules. Third property is vapor pressure. It can be explained as, consider a closed cylinder with a liquid inside it. During evaporation, the molecules of the liquid are trapped in the bottle. The molecules which convert to vapor state may hit the liquid again and join it by condensing into liquid. When the rates of these 2 processes become equal, the pressure exerted by the vapors is called vapor pressure. Now, moving on to the factors affecting vapor pressure. Number 1. Nature of liquid. Vapor pressure of a liquid depends upon the nature of liquid. That is, liquid having low boiling points exert more vapor pressure. Number 2. Temperature. Vapor pressure of liquid increases with the increase of temperature. Due to increase of temperature, the kinetic energy increases, and the liquid is changed into vapor. As a result, vapor pressure of the liquid increases. Number 3. Intermolecular forces. The liquid in which intermolecular forces of attraction are weak show high vapor pressure. Number 4. When a liquid is heated, the rate of evaporation of the molecules also increases. When the pressure of the liquid becomes equal to the atmospheric pressure, the liquid starts boiling, and this temperature is known as the boiling point of the liquid. If the external pressure on a liquid is changed, the boiling point of the liquid also changes. The increase in external pressure decreases the boiling point. That is why water boils quickly on high places. In the previous video from our chemistry section, we started the topic 3 states of matter and discussed the liquid state. In this video, we will talk about the solid state of matter. So let's start. Solid state is the state of matter in which atoms, molecules or ions are held together by strong attractive forces due to its strong, attractive, interatomic, molecular forces. The particles of solid cannot move. However, they possess some vibrational energy. Solids have both definite shape and definite volume. According to the kinetic molecular theory of solids, the molecules of solids are present at fixed positions and are unable to move. This is because the particles in a solid are closely packed due to a strong, attractive forces between them, and also because they have a strong, attractive forces, they have definite shape, because the particles are arranged in a fixed pattern. Solids are classified into two types. Number 1, crystalline solids. Number 2, amorphous solids. If the particles are attached to each other with a definite arrangement and a solid possesses a definite geometrical shape, then these type of solids are called crystalline solids. Examples: graphite, diamond, etc. If the particles are attached to each other without definite arrangement, so they do not have a definite shape, the particles of such solids have a random three-dimensional arrangement. Examples of amorphous solids are glass, rubber, plastic, etc. Now moving on to the properties or behavior of solids. Number 1, diffusibility. Diffusion also occurs in solids, but at a very slow rate. If a polished piece of zinc is clamped with a piece of copper for a long time, after a few years, we will see that some particles of copper have penetrated into zinc. It shows that diffusion in solids is possible, but it occurs very slowly. Number 2, compressibility. The compressibility of solids is nearly zero in terms of kmt. The particles of solids are so tightly bound together that only a little space is left. So we can say that by applying pressure on solids, no change in volume is observed. So the solids are compressible to a negligible extent. Number 3, sublimation. The property of some solids. Det on heating. These solids are directly converted into vapors without liquefaction, meaning they directly change into gas without changing into a liquid. This property of solids is known as sublimation. Examples of solids which are sublime: dry ice, that is solid CO2, NH4Cl, I2, etc. Number 4, melting. In terms of kinetic theory, when solids are heated, vibrational energy of the particles increases, until at melting point some particles are vibrating with sufficient energy to overcome the forces holding them. Hence, they become mobile, that is, solid fuse. Gases are all around us, from the air we breathe to the fuel that powers our vehicles. But what exactly is a gas, and how does it differ from other states of matter? In today's video, we will learn about the gaseous state of matter. So, without further ado, let's start. Gases are made up of atoms and molecules that are in constant motion. Force of attraction between the particles is negligible, and they can move freely. They have no fixed shape or volume, and will expand to fill any container they are placed in. This is why a balloon will expand as more air is pumped into it, because the air molecules are taking up more space as they move around. Gases show 3 types of behavior: compression, diffusion, and pressure. Number 1, diffusion or diffusibility. It is the movement of molecules from a region of higher concentration to a region of lower concentration. The best example of diffusion can be perfume or spray. When sprayed in one part of a room, yet soon it diffuses so that you can smell it everywhere. In this case, the spray or perfume bottle is higher concentration while the room is lower concentration. Number 2, compression or compressibility. Gases are easily compressed because the molecules have so many empty spaces between them that by applying pressure, the molecules come closer. which is why they can be stored in containers like gas cylinders. When the lid or valve of a container is removed or opened, the gas molecules expand and escape. The examples can be LPG cylinders or oxygen cylinders. Number 3. Pressure. Gas molecules have high speed and random motion, due to which they collide with each other and walls of container, and thus exert pressure on the walls of container. The example of pressure can be airplane wings, which are shaped to make air move faster over the top of the wing. When air moves faster, the pressure of the air decreases, so the pressure on the top of the wing is less than the pressure on the bottom of the wing. The difference in pressure creates a force on the wing that lifts the wing up into the air. Gases also play a vital role in many natural processes, such as the burning of fossil fuels that powers our cars, and the nuclear reactions that take place in the sun, which provide us with light and heat. So next time you light a stove or inflate a balloon, remember the properties of gases and the important role they play in our daily lives. Thank you for watching. Hope you enjoyed the video. Drop down your feedback in the comment section. And lastly, don't forget to like, share, and subscribe to our channel. Stay tuned for more upcoming content. Till then, take care.
Hello everyone, have you seen before that we have talked about different topics in our previous videos? Our topic for today will be about summarized history of physics. Physics has become an essential part of a human being. Elements of what became physics were drawn primarily from the fields of astronomy, optics, and mechanics, which were methodologically united through the study of geometry. Physics is a branch of science whose primary objects of study are matter and energy. An example of basic physics would be the conversion of mechanical energy into electrical energy to light up a bulb. But physics isn't just limited to some examples, rather it's divided into many branches. There are two main branches as of today, classical and quantum or modern physics, and then there are some other sub-branches of physics such as nuclear, astro, bio, electronics, fluid mechanics, etc. Similar to the number of branches, there are many notable people that have contributed to the development of physics. One of them names would be of Ibn al-Hashim, who is considered to be the father of modern scientific method and also the founder of modern optics. He was a physicist. He developed laws of reflection and refraction. Another name would be of Abu Rayhan al-Biruni. He was an astronomer, physician, and mathematician. He was the first able to obtain a simple formula for measuring the Earth's radius. According to Stephen Hawking, Galileo, perhaps more than any other single person, was responsible for the birth of modern science, a composite montage comparing Jupiter and its 4 Galilean moons. Physicist, mathematician, astronomer, and inventor Christian Huygens was the leading scientist in Europe between Galileo and Newton. He has been referred to as the leading actor in the making of science in Europe. Newton invented one form of an entirely new branch of mathematics, calculus, which was to become an essential tool in much of the later development in most branches of physics. Newton also built the first functioning reflecting telescope. German physicist Albert Einstein showed how measurements of time and space are affected by motion between an observer and what is being observed. Einstein proposed that gravitation is a result of masses or their equivalent energies, curving or bending the spacetime in which they exist, altering the paths they follow within it. Talk about quantum mechanics, then there is Max Planck, who was awarded the Nobel Prize for the discovery of energy quantum. New principles of quantum rather than a classical mechanics formulated in metrics form by Werner Heisenberg and Max Born
and Pascal Jordan in 1925. Heisenberg was awarded the 1932 Nobel Prize in Physics for the creation of quantum mechanics.
We will be discussing some scalar and vector quantities and some fundamental quantities of motion. This video is a build-up to our next video, which will be about equations of motion. So before that, we need to discuss some properties. So let's start. Scalar quantities are quantities that are described by a magnitude, or you can say a value, a number. They do not have direction of action. For example, 10 centimeters, 50 seconds, 7 liters, and 3 kilograms. Vector is a term that refers to some quantities that cannot be expressed by a single number. That is, vectors are quantities that have both magnitude and a direction. They are represented through an arrow. Now moving on to our second topic, which is motion. An object is said to be at rest if it does not change its position with respect to its surroundings with time. The examples of rest include stopped cars, sitting, standing, fixed clock, etc. An object is said to be in motion if the position changes with respect to its surroundings and time. The examples of motion include running, moving vehicles, swimming, etc. Now talking about types of motion. Number 1, translatory motion. Motion in which all points of a moving body move uniformly in the same direction. For example, motion of an arrow from the bow. Number 2, rotatory motion. The motion that occurs when a body rotates on its own axis. For example, the motion of the Earth about its own axis, fan blades, Ferris wheel, etc. Number 3, vibratory motion. When a body moves to and fro about its mean position is called vibratory motion. The examples are pendulums, swings, tuning forks, etc. Moving on to distance and displacement. Distance is the total movement of an object without any regard to direction, while displacement is defined as the change in position of an object with respect to direction. Distance is an scalar quantity, while displacement is a vector quantity. Their unit is meter. Now, for example, take 2 points A and B. The gray and yellow line shows distance, while the white one is displacement, because the gray and yellow one are 2 random paths to point B, while the white line specifies a direction. Speed. The distance covered by a body in unit time is called its speed. It has no particular direction. Mathematically, speed equals total distance covered upon total time, or V equals S upon T. It is a scalar quantity, and its SI unit is meter per second or meter second inverse. Uniform speed. If a body covers equal distance in equal interval of time, that is, you can say 1 meter covered in 1 second. Velocity. The rate of change of displacement is called velocity, or you can say that the distance covered in unit time by a body in specified direction is called velocity. Its formula is change in displacement upon time taken, or V equals delta D upon T. It is a vector quantity. Uniform velocity. If a moving body covers equal displacement in equal interval of time, its SI unit is same as that of speed. Acceleration. The rate of change of velocity is called acceleration. Can be calculated as acceleration equals change in velocity upon time taken, or equals Vf minus Vi upon t, where Vf is final velocity, Vi is initial velocity, and t is time taken. Acceleration is a vector quantity. Its SI unit is meter per second square. When the direction of velocity and acceleration is in the same direction, it is positive acceleration, and if it is in the opposite direction, then it is negative acceleration or deceleration. Today we will talk about the equations of motion. In our previous video from our physics series, we discussed some quantities, which we'll be using to derive the equations. So, if you haven't watched that video yet, you can find the link in description. So without further ado, let's start. For the first equation of motion, consider a body which is moving with an initial velocity of vi. After an interval of time t, the velocity of the body changes to vf, or the final velocity of the body. For the change in velocity, we will subtract initial velocity, vi, from the final velocity, vf. Rate means change with respect to time. So, the rate of change in velocity means dividing time, t, by vf minus vi. But by definition, rate of change in velocity is acceleration. Therefore, a equals to vf minus vi upon t. T is dividing on the right-hand side, so we will send it to the left, where it will then multiply to a. Since vi is subtracting on the right side, we will send it towards left, where it will add to a t. Now, the equation becomes vf equals to vi plus a t, which is the required first equation of motion. For the second equation of motion, consider a body which is moving and changes its position and covers a distance, s, in time, t, in a particular direction. Also, if the total displacement, s, is divided by the time, t, we get the average velocity. v equals to s upon t. We will send the dividing t from the right side to the left. The equation becomes s equals to vt. Suppose it's our equation 1. Also, the average velocity, v, equals to vf plus vi upon 2. Suppose it's our equation 2. Now substitute equation 2 in 1. That is, place the value of v in equation 1. Then the equation becomes s equals to vf plus vi upon 2 multiplied by t, which is our equation 3. Using first equation of motion, vf equals to vi plus a t, which becomes our equation number 4. Now put equation 4 in equation 3. That is, the equation becomes s equals to vi plus a t plus vi upon 2 multiplied by t. Add both vi. The equation becomes s equals to 2vi plus a t upon 2 multiplied by t. Now break the LCM, and then the equation becomes s equals to 2vi upon 2 plus half a t multiplied by t. The 2 will be cancelled since there is one multiplying and other one is dividing. In the end, the equation will be multiplied by t, and the equation will become s equals to vit plus half a t square, which is our required second equation of motion. Consider the same body for third equation of motion, and we will repeat the same steps till equation 3 as we did in second equation of motion. After that, we know a equals to vf minus vi upon t. We will cross multiply a and t, which will then become our equation number 4. Put equation 4 in equation 3, that is, s equals to vf plus vi upon 2 multiplied by vf minus vi upon a. Then use the mathematical formula a plus b into a minus b equals to a square minus b square. S equals to vf square minus vi square upon 2a. Since 2a is dividing on the right-hand side, we will send it to the left, where it will then multiply to s. The final equation becomes 2as equals to vf square minus vi square. This is the required third equation of motion. Welcome back, learners. We hope you're all doing great. Today, we will learn about something you all have heard somewhere. The famous Newton's laws of motion. We will discuss the first law in this video, and the remaining 2 in coming ones. So, without further ado, let's start. What are Newton's laws of motion? Sir Isaac Newton in 1686 presented as 3 laws of motion. These laws describe the relationship between motion of an object and the forces acting on it. These laws laid the foundation for classical mechanics, which is the study of motion of bodies, also including special cases where bodies remain at rest. First law states that an object continues its state of rest or its state of uniform motion unless an external force compels it to change its state. The explanation for this law is that a body in uniform motion or in a state of rest cannot change or decrease without the effect of a force. This tendency to resist the change in motion is called inertia, which is the property of a body to continue to move in a straight line at a constant speed. That is why this law is also known as law of inertia. Let's see some examples to understand things better. When you're in a moving bus, and the bus suddenly stops, people fall forward. Do you know why? Because your body and the bus were going in the same direction. But when the driver hit the brakes and the bus stopped, your body was still going in the same direction. That is the reason behind people falling forward. And this resistance of change in motion is called inertia. Another example can be jumping from a moving vehicle. Your body will go in the direction in which the vehicle was moving. Also, when you turn of a fan, it continues its circular motion before coming to a stop. Now, let's see some animated examples. See this car. It is moving on a straight path with a uniform velocity, and it will continue to do so until and unless a force is applied, which can be the brakes to stop it. Also, a body at rest, such as these stones, will continue to be in their state of rest until an external force is applied on them to move. Hello learners! Welcome to the biology series. Today's video is all about a recapitulation of biology and living entities. The term biology was coined by Lamarck and Treviranus. Well, biology is the process of studying life in a scientific way. In order to understand life on Earth, biology is an important facet of science that provides information about various life forms. For that, we need to characterize living things from non-living things. A feature that could be used to decide whether something was living or not would be called a characteristic of living things. Certain features are common to all living things. They can grow, reproduce, react to surroundings, move, excrete, obtain nutrition, respire, and are cellular. An object must possess all these characteristics to be considered living. Otherwise, it is not a living thing. As we have studied the features of living things, one of them is that all living things are made up of cells. What is cell? Cell is a basic, structural, and functional unit of life. An organism may have single or multiple cells. As the name implies, unicellular organisms are made up of a single cell, while multicellular organisms have carried many cells to perform life processes. Moving forward, let's talk about types of cells based on cellular structure. These are prokaryotic cells and eukaryotic cells. Prokaryotes are the simple, single-celled organisms that do not have a true nucleus. For example, bacteria, mycoplasma, cyanobacteria, etc. While eukaryotes are the complex, multicellular organisms that possess true nucleus. For example, humans, plants, etc. are considered eukaryotes. Let's have a look at levels of structural organization in the living body. Living organisms are highly complex, ordered systems made up of single or multiple cells. The atom is the smallest and most fundamental unit of matter. The bonding of at least 2 atoms or more form molecules. In multicellular organisms, similar cells form tissues. Group of tissues constitute organs. An organ system is made when organs work together. When organ systems are arranged properly to complete a particular task, make up an organism. The cell theory is one of the fundamental theories of biology. This original theory was proposed by Schleiden and Schwann in 1838, which states that all living things are made up of cells and arises from pre-existing cell. Later on, the original theory was expanded by the scientists, and it was named as modern cell theory, which states that energy flow occurs within cells. Cells contain genetic material and that all cells are essentially the same in chemical composition. Continuing ahead, let's have a brief look at scientists and their discoveries.
Take a look.
The first compound microscope was invented in 1519. In 1665, Robert Hooke redesigned the existing compound microscope. Through this microscope, he discovered cells in the piece of cork. Later on, he illustrated his observations in a book named Micrographia. After Hooke's discovery, Dutch scientist Antony van Leeuwenhoek discovered other tiny organisms. That's bacteria and protozoa. He called these tiny creatures animalcules. Marcello studied animal tissues under microscope. Nehemiah Grew described plant tissues. Fontana found nucleolus in the skin cell of eel. Robert Brown discovered nucleus. However, Schwann and Schleiden studied plants and animals' tissues, respectively, and proposed the cell theory.
Trivia time.
Do you know? There are more bacterial cells in the body of human than human cells. The largest living cell in the nature is ostrich egg. In the previous video, we discussed about the introductory part of cell and biology. The branch of biology that deals with the cell and its organelles is known as cytology or cell biology. This video focuses on the cell organelles. A typical eukaryotic cell has three major parts: plasma membrane, cytoplasm and its organelles, and nucleus. The fourth component, cell wall, is present in plant cells and fungal cells. The main difference between the prokaryotic cell and eukaryotic cell is the presence of a nucleus, and in eukaryotic cells, DNA lives in the nucleus and directs the synthesis of ribosomes and proteins. The nucleus is the control center of the cell which stores the genetic material DNA. It is the most evident organelle in the cell, and happens to be the home for some important cellular processes. The nucleus is surrounded by two phospholipid bilayers. The boundary of nucleus is called nuclear envelope, which is embedded with nuclear pores which allow substances to enter and exit the nucleus. There are three components of nucleus. The nucleus stores chromatin in a gel-like substance called the nucleoplasm, while nucleolus is a conspicuous, rounded, non-membrane bound body within the nucleus of a cell. Chromatin network is a complex of DNA, RNA, and proteins within the cell nucleus, out of which chromosomes condense during cell division. Nucleic acid is a chemical proteinous compound found in nucleus. There are two types of nucleic acid, RNA and DNA. Transcription occurs in the nucleus because eukaryotes store the DNA in the nucleus. To understand chromatin, it is helpful to first consider chromosomes. The nucleoplasm contains nucleoli and a network of thread-like structures called chromatin network. Each thread of chromatin network is called chromosome. Chromosomes are structures within the nucleus that are made up of DNA, the hereditary material. Chromosomes are only visible and distinguishable from one another when the cell is getting ready to divide. A chromosome consists of two parts, chromatids and centromere, where chromatids are the arms which are joined with the help of centromere. On the basis of position of centromere, chromosome has four types: metacentric, submetacentric, telecentric, and subtelecentric. The plasma membrane, also known as the cell membrane or cytoplasmic membrane, is a biological membrane that separates the interior of a cell from its outside environment. Despite differences in structure and function, all living cells in multicellular organisms have a surrounding plasma membrane. It is the outermost covering of animal cells, but in plant cell, lies next to the cell wall, which is composed of a phospholipid bilayer with embedded proteins. The plasma membrane is selectively permeable to ions and organic molecules, and regulates the movement of substances in and out of cells. It regulates the transportation of molecules across the membrane, and communicate with other cells via protein receptors. If you look at the diagram of a plant cell, you will see a structure external to the plasma membrane called the cell wall. Cell wall is a non-living and strong component of cell, located outside plasma membrane. The cell wall contains not only cellulose and protein, but other polysaccharides as well. The cell wall provides structural support and protection. The cell wall also prevents the plant cell from bursting when water enters the cell. In animal cells, cell wall is absent, while in plants and prokaryotes the cell wall lies before the cell membrane. Does a cell have, or even need, a skeleton? The answer is yes. Within the cytoplasm, besides organelles, ions, and organic molecules, there is a network of protein fibers that help maintain the shape of the cell. The cytoskeleton is a cellular scaffolding or skeleton that crisscrosses the cytoplasm. There are 3 types of fibers within the cytoskeleton: microfilaments, intermediate filaments, and microtubules. Cytoskeleton maintains cell shape, secures organelles in specific positions, allows cytoplasm and vesicles to move within cell, and enables unicellular organisms to move independently. All eukaryotic cells have a cytoskeleton, and recent research has shown that prokaryotic cells also have a cytoskeleton. The cytoplasm consists of everything inside the plasma membrane of the cell. A Swiss biologist named Rudolf von Kleiker coined the term cytoplasm. The cytoplasm is the entire region of a cell between the plasma membrane and the nuclear envelope. It is composed of organelles suspended in the gel like cytosol, the cytoskeleton, and various chemicals. Glucose and other simple sugars, polysaccharides, amino acids, nucleic acids, fatty acids, and ions are also found in the cytoplasm. Many metabolic reactions take place in the cytoplasm. Eukaryotic cells differ from prokaryotic cells, as prokaryotic cells don't have a defined nuclear membrane, so the cytoplasm fills the whole space bounded by cell membrane. Do you know? New research suggests that the traditional definition of cytoplasm is no longer valid, as evidence is proof that cytoplasm is similar to glass-forming liquids. Ending this part here with the hope that you not only understand it, but also liked it. If you do so, stay tuned. Till then, take care. Thank you for watching. In our previous video of tenses we discussed the simple or indefinite type, and today we will be talking about the continuous type of tenses. So let's start. As you know, there are 3 types: present, past, and future continuous. First, present continuous. The structure for affirmative is subject plus helping verb, which is or am or are, then verb first form with ing and then ending it with object. For example, am doing my homework. We are going to play basketball ball. She is helping her mother in the kitchen. If we talk about negative, then we keep the same structure as affirmative. Just add not after or with the helping verb. For example, I am not going to school today. He is not playing outside. They are not going to attend the graduation ceremony. In interrogative, we start the sentence with the helping verb and then subject. Verb first form with ing, then object, and in the end question mark. For example, is he coming to attend the class today? Are they going to study with us? Am I going to do fine today? Interrogative is the combination of interrogative and negative sentences. We'll use the helping verb in the beginning. The only difference is that we will add not after subject. For example, is he not going to attend the party today? Are we not going to the park? Am I not going to take a shower? Moving on to past continuous. The structure remains same. Just the helping verb here are, was, and were. For example, he was planning to study abroad. They were going to play outside, but it started raining. We were making the strategy for today's game. In negative, as you know, we will just add not after the helping verb, as you can see in the examples given below. In interrogative, we'll start with helping verb and end the sentence with question mark, as it is the most important part of the interrogative sentences. The examples for past continuous interrogative would be, was he not eating the meal? Were they not working in the factory? Was she not singing a song? Now our last topic, the future continuous tense. Here the helping verbs are will be and shall be. Shall is usually used with only subject, we, but you also use will, it's not mandatory. For example, I will be attending the seminar. He will be completing his summer homework. We shall be working together on this project to produce better results. In future, continuous negative, we will add not before be. That is, the helping word would become, will not be. For example, she will not be cooking the dinner tonight. I will not be coming to your party. They will not be playing outside today. If we talk about future continuous interrogative, then we will start with the helping verb, then subject, and after that, add, be. For example, will he be coming to school today? Shall we be studying hard? Will they be rehearsing for the drama? For interrogative, we can see some examples such as, will they not be sleeping right now? Will you not be practicing for the upcoming math exam? Will he not be waiting for me at the bus stop? Hope you all are doing great. Our topic for today will be from the English portion, and we will be talking about the perfect type of tenses. If we talk about the perfect type of tenses, then it means the use of third form of verb. So let's start the video and learn the perfect type of tenses. First comes the present perfect tense. In present perfect tense, the helping verb are has or have. The structure for the affirmative sentence is subject plus helping verb plus verb. Third form plus object. We use has with singular person and have with plural person. The examples can be, they have spent all the money. We have made a beautiful painting. He has finished the work, etc. Now present perfect negative. The structure is subject plus helping verb plus not plus verb. Third form plus object. The examples are, she has not eaten the meal. I have not broken the cup. You have not answered to any of my calls. Now, moving on to present perfect interrogative. The structure for it is helping verb plus subject plus verb. Third form plus object plus question mark. The examples are, has he brought his camera with him? Have the kids eaten their food? Have we ever won a prize? Etc. Next up is past perfect tense, and the helping verb is had. For the affirmative, the structure is subject plus helping verb plus verb. Third form plus object. The examples can be, we had watched this movie 3 years ago. He had bought a car last year. The bus had gone before I reached at the stop. If we talk about past perfect negative, then the structure is subject plus had, plus not, plus verb, third form plus object. The examples are, he had not received my letter, they had cleaned their room, we had not played cricket this week, etc. Past perfect interrogative. The structure is had plus subject plus verb, third form plus object plus question mark. The examples can be, had he prepared himself for the exam? Had they come on time? Had you taken the medicine when you were ill? Etc. Last is future perfect tense. The helping verb used is will have. The structure is subject plus will have plus verb, third form plus object. For example, she will have completed this work next week. They will have attended the meeting. I will have reached my house, etc. Now, future perfect negative. The structure is subject plus will plus not plus have plus verb third form plus object. Since it is negative, we will use not, and as you can see, the helping verb will have will be broken into two parts and not will be used in between. For example, he will not have completed his assignment, they will not have enjoyed the party, she will not have reached her house, etc. The last tense we will be covering is future perfect interrogative. That is, structure for it is, will plus subject plus have plus verb, third form plus object plus question mark. Since it is an interrogative sentence, the use of question mark is must. The examples are, will he have helped out the needy? Will the police have caught the criminals? Will she have met her friend? Etc. Welcome back. Today, we will learn about the perfect continuous type of tenses. In our previous 3 videos we have talked about indefinite tenses, continuous tenses, and perfect type of tenses. So, if you haven't watched those videos yet, be sure to check them out first. First comes the present perfect continuous tense. It shows the ongoing nature of an action that started in the past and is still continued in the present. For this purpose, a time reference is also used to show when the action was started or for how long the action is being continued. Since is used when the exact starting time is given, and for is used when only the duration of the action is known. The structure for present perfect continuous is subject plus helping verb, which is has been and have been, then verb first form plus ing, and in the end object, which here is since or for plus time. For example, I have been working on this project since December 2022. Here, since is used because exact starting time is given, which is December 2022. He has been staying up late for 3 days. They have been playing cricket for 2 hours. Here for is used because only the duration is given, not the exact time. Keep in mind, has been is used with singular person, which are he, she, it, name, and have been is used with plural person, which are I, we, you, they. In negative, same structure is followed as affirmative. The only difference is that word not is added between has or have been. Then the complete helping verb becomes has not been or have not been. For example, I have not been using my car for 6 months. You have not been attending your lectures since 9th March. She has not been feeling well since 2019. In interrogative, we will break the helping verb and will use has or have in the start, that is before the subject, while been will come after the subject, and last, but not the least, question mark will be used in the end. For example, has he been living in USA since 2021? Have they been completing their homework since 5 p.m.? Have you been writing this report for 3 days? Next is past perfect continuous tense. It states the continued nature of an action which started at some point in past, continued for some more or less specific time in past. It also requires time reference, and for that same words since or for are used. The structure for past perfect continuous affirmative is subject plus helping verb had been plus verb first form with ing plus object, which here will be since or for plus time. For example, I had been sleeping late at night for 3 days. We had been playing outside for 3 hours. She had been cooking the dinner since 8 p.m. In negative, we will only add the word not in between the helping verb. That is, the helping verb then becomes had not been. For example, he had not been staying at the hotel since last Wednesday. You had not been taking care of yourself for 3 days. They had not been watching this movie since 11 p.m. In interrogative, we will use had first, then the subject, and after that, been. In the end, don't forget to use the question mark. Examples are, had he been going to school since Tuesday? Had the patient been taking his medicine for 5 days? Had they been selling chairs since April 2010? Next is future perfect continuous tense. It states the actions which are assumed to occur in future and to continue for some more or less specific time in future. The specific words since and for are used in the sentence to show the time of action. The structure for future perfect continuous affirmative is subject plus helping verb will have been plus verb first form with ing plus since or for plus time. Examples can be, she will have been teaching the students for 7 months. We will have been going to the library since Monday. The kids will have been studying this book for 3 hours. For future perfect continuous negative, we will add word not in the helping verb. Then it will become will not have been, while rest of the structure remains same. For example, she will not have been going to college since Friday. He will not have been playing cricket for 3 days. We won't have been using our computer for 6 hours. As you can see here, will not have been can be shortened to won't have been. In interrogative, will is used before the subject while have been is used after the subject, and a question mark is used in the end. Examples are, will the patient have been taking his medicine for 5 days? Will she have been studying in a new college since December? Will the kids have been playing with toys for 2 hours? Thank you for watching. Hope you learned something from the video, and if you did, be sure to give a thumbs up. Your feedback is appreciated in the comments section below. Lastly, don't forget to subscribe our channel, since there will be new things coming your way. This was a compiled video for all the topics we have discussed up till now. Take care and stay tuned for more upcoming content.